Let's talk about present value. Now, this is a really simple bit of math, and we can make it a little bit more complicated. And actually, you know what? I encourage you to look into things like continuous compounding and related concepts. But really, we're going to stick with just this one simple equation for this semester, right? We're really just concerned with the intuition, right? We want to get a handle on the basics here and not get bogged down in the details. So what this equation does is it lets us basically move through time, and using some simple rules of algebra, we can rearrange this and we can figure out interesting questions, right? We can ask about not just what will we get after compounding interest, but what do we need right now to get some amount after some compounding interest. So with this basic equation, we're going to be able to do things like ask the question, how much is a dollar worth 100 years from now compared to right now? We're going to ask questions like, what is the value of a winning lottery ticket that promises $1 million a year for 30 years? And it's all going to come from this really simple equation. So let's go ahead and do the most interesting thing. Well, actually, let's take a quick look at what it is first, right? And then we'll say, really, this is what we're going to get to. Present value we'll get to over here. But if we're looking at something like you put $100 in the bank and you're getting 5% interest, then after 1 year, we can say 100 times 1.05, you're going to have $105 when we include the interest. Right? Nothing too crazy. You're familiar with this basic intuition. You've seen it a million times. Now, if you go away and you leave your money for another year and get another 5% interest, now you're getting this amount, but you're getting interest on it. So now you're getting $105 and you're getting another year's worth of interest there. Well, let's see, how much is that going to be? That's going to be still 100, still 5 from your first year's interest, plus 5 years from your second year's interest on that $100, and then plus you're going to have interest on that first year's growth, right? So maybe I should have colored these as here is that interest from the first year, and now we're going to have an extra 5% of that. 0.05 times 5. It's not a whole lot, but it's something. And as we let time get bigger, this is going to expand. Right? So basically, we're just multiplying something to account for some interest rate, and then we're multiplying it again and again and again for as many years as we leave it. And that's finally going to give us how much we end up with. Now, more interesting than that is to take some target and figure out how much do we need to put away now. So future value equals present value times 1 plus r to the power of t. Well, all we have to do is divide 1 plus r to the power of t, and that's going to give us present value. Present value equals future value divided by this. And actually, there's a convenient rule of exponents that lets us say it's 1 plus r to the power of negative t. These two statements are equivalent. So we can ask questions about r and t, but really we're most often going to be interested in taking some figure and making it comparable to some figure today. So if we're to ask a question like, we're considering some policy, right? Policy X, and it's going to cost, let's say, $1 trillion right now. But the benefit, $1 trillion, make that clear, $1 trillion cost right now. But the benefit is, let's say, $2 trillion in 30 years. should we do it? Right? So you might think about something like expanding investment in pre-kindergarten education. What are we going to get? Well, we're going to get something. Well, we're going to get something now, right? We're going to have some kids taken care of during the day, but the hope is that we get some longer run benefit. And then the question is it worth it? So we're going to need to do some figuring here. So let's think about how much that benefit is now. So that's the future value. So we'll say 2 for 2 trillion times 1 plus r. Now here we need to make an assumption. What is a reasonable figure to put in there? But t we've got, that's just minus 30. So this is the present value of the cost. Actually, sorry, this is the present value of the future benefits. So we could call this the discounted present value of those future benefits. Right? But just say present value equals 2 times 1 plus r to the minus 30. And we really want to make sure that we don't do this unless the benefits exceed the costs, which is $1 trillion. Since that's right now, we could even put it in these terms. Right? We could say, well, what about if it's in 1 year? Right? Then we'd say $1 trillion times 1 plus r to the power of 1. But if it's right now, we would just say to the power of 0. And anything to the power of 0 equals 1, which is a nice little feature of math. So this just says 2 times 1 plus r to the power of negative 30 is greater than $1 trillion now. So let's ask the question about how big does r need to be? Right? So if r is really small, what this is going to boil down to, now, yeah, let's look at it in this term, right? So we've got the future value is 2, and then we're dividing by something multiplied by itself 30 times. So let's say r was 0. Then we would have 1 times itself 30 times, and we just have 2 over 1. All right, so what does that mean? Well, that would mean that this looks really good. But what does it mean to have an r of 0? That means we're saying that there is, basically, we could take this $1 trillion and we could, our next best alternative to doing something like this might just be to bury it in coffee cans in our backyard and get 0% interest. But what if we could take that $1 trillion and just put it on the stock market? Right? What would happen if we were, say, getting 10% interest on that? Well, if we were getting 10% interest on that, then we've got 1 times 1.1 to the power of 30 is going to give us sort of our alternative. Right? So if that's our alternative, is this a good deal? Right? So if we think that basically the opportunity cost of putting the money up now, the opportunity cost of the time would be 10% if we're thinking that this is the relevant alternative. And in that case, we're going to have a much bigger number down here. So we're going to have 2 divided by something, right? Look, before we had 2 over 1. What if we had 2 over 4? Well, now this is 1/2, which is not bigger than 1, right? So in that case, if r is too high, there's going to be a point where this sort of a program would no longer make sense. Now, I'm not even going to worry about the numbers right now because this is the sort of thing that we really should just have the computer do. But here's the basic intuition. Again, we've got our simple equation that tells us how money compounds, how something can grow over time. Now, of course, I say money, but it could be something like skills. You invest in knowledge now, which allows you to build more knowledge in the future and more knowledge after that. Knowledge definitely has compound interest. Populations grow at a rate, right? An exponential rate. So after several years of, say, leaving some leftovers in the back of my fridge, I can talk about the population of mold living on that as having similar logic to here. Right? The mathematical structure is basically the same. Now we take that structure, we rearrange it. It looks like we just kind of flipped some stuff, but we did a little bit of algebra to get to present value equals future value times 1 plus r to the minus t. And what this allows us to do is to just plug in values to make comparisons, to ask questions like, is this long-run project really worth it? Or how much is that project really worth in terms that make sense today? All right, let's stop here